Welcome to part 2 of the Phantastic Physics Bridge Design tutorial. So remember, in part 1, we finished finding these two reaction forces and we got 3,500 pounds supporting the left side of this bridge and 4,500 pounds supporting the right side. And so now in part 2, which is what we're going to do today, we're going to figure out exactly how much tension or compression is inside each of these bridge members. Okay, so stick around and find out how to do it. Now, this is where it gets interesting. Now that we know our two reaction forces at our two supports, we're ready to actually start analyzing each joint of this bridge to figure out what these internal member forces are. So how much tension and compression is either squeezing or pulling these members apart, okay? And so what I like to do is start at the joint with the least amount of traffic. So for example, if I look at joint B, there's actually 1, 2, 3, 4 members all coming together at that joint. And remember, each member has an unknown force inside it. So that means there's 4 unknown forces at that joint. But if you recall, we only have access to 2 equations at that joint. Some of the forces in the x direction and some of the forces in the y direction. So if we have 4 unknowns and only 2 equations, there's no way we're going to be able to start at joint B. Similarly, if we started at joint E or joint D, there's 3 members meeting at those joints, 3 unknowns, but again, we only have 2 equations, so that's not enough. We can't start there either. That leaves us with only 2 options. We can start our analysis at joint A or at joint C. Now, I like to start on the left side, so I'm going to start at joint A, but technically C is just as valid of a choice. So I'm going to write joint A just to show where we are. And now I'm just going to draw that joint. So the joint looks like this. I'm going to label that A. And I'm going to add all the forces that are acting at joint A. So I know there's a 3,500 pound reaction force that's pushing straight up. So I'm going to label that 3,500 pounds. I also know there's this member AB, and that member might be in tension and it might be in compression. I actually don't know yet. So I'm always going to assume tension. And the reason I'm assuming tension is I'm going to draw it pointing away from this joint. So I'm saying member AB is a force that's pulling on joint B. It's pulling it away, and that's modeling this member being in tension. We're showing it as a force that's pulling on joint A. Member AE, I'm also going to assume is in tension. So I'm showing it pulling on joint A. Now, if these members were in compression, I would have drawn them the other way. Instead of pulling away from the joint, they would be pushing against the joint. Now, it may turn out that these are in compression. I don't know yet. But when I do my calculations, if I get a negative answer for one of these, that tells me my assumption of tension was incorrect, and it's actually the other way around, and really it's in compression. So no matter what, we're still going to get the right answer. Now, we also know that there's an angle of 60 degrees right here. And so there's my joint. Joint A has a reaction force of 3,500 pounds, and it has 2 member forces pulling away from the joint. We're assuming tension for now, so that we're going to call those forces force AB and force AE. And those those numbers, they signify the letters of the 2 joints that the members hit, okay? So there's our forces. Now we have to do a little side note here, because look at this member AE. Remember how we only have 2 equations, sum of the forces in the x direction that deals with horizontal stuff, and we have the sum of the forces in the y direction, which deals with vertical stuff. But force AE is neither horizontal nor vertical. It's a diagonal force. And so what do you do when you have a diagonal force? Well, we have to use a little bit of trigonometry here. And so if you imagine this dashed line is like a reference point, and we know this is a 60-degree angle, any diagonal force can be broken into components. So a diagonal force is made out of an x component, or the x part of this force, which we could call F sub x, and a y component, which we can call F sub y. So according to trig, Fx and Fy are the 2 components that make up this force F. So it has an x component and it has a y component. So what is Fx and what is Fy? It's simple. Fx is this force, whatever it is, let's say 50 pounds, times the cosine of this angle. So times the cosine of 60 degrees. And Fy is equal to this force, whatever it is, times the sine of this angle. So times the sine of 60 degrees. And so that's always going to be true. Any diagonal force can be broken into an x and y part. And once we've broken them into x and y pieces, we can actually analyze them using our two equations, okay? So going back to our main problem here, we have this force AE, and so we know that AE can be broken into AEX. I'm going to draw that in red because this is the component, the x component of force AE, and AEY. This is the y piece, or the y component of this force AE. So what I've done is I've changed a diagonal force into an x component and a y component, okay? So now I'm ready to start analyzing. So first question I have for you, audience, is how many forces in the x direction do you see on this diagram now? Well, there's two. I've got force AB, which is the force in member AB, and I have this force AEX, which is the x component of this force AE. So I have two total x forces. How many y forces do you see? I have this 3,500 pound force pointing upward, and I have this AEY, the y component of this force AE. So two y forces and two x forces. But both of my x forces are unknowns. So I can't start with sum of all forces in the x direction. This equation is not going to work because there's two unknown x forces. So that means instead, I'm going to start with this equation. Sum of all forces in the y direction equals 0. And so we have 3,500 pounds. That's a positive because it's upward. And we also have what? AEY. So plus AEY, and that all equals 0. Sum of all forces adds up to 0. Well, what's AEY? Remember, according to trigonometry, that's force AE times the sine of this angle, 60 degrees. And all that still equals 0. So I just replaced AEY, this y component of that force, with AE sine 60, because that's the same thing, okay? And so now I can say AE, the actual force of this member is, and I'm going to subtract 3,500, so it's on the other side of my equation. And then I'm going to divide both sides by the sine of 60. And so just through a little bit of algebra, subtracting this over, dividing both sides by this number, we can actually solve for this force. And that will be one of our member forces, okay? So we have negative 3,500 divided by the sine of 60. Take out my calculator. Negative 3,500 divided by sine 60. And I get negative 4,041.45 pounds, okay? So the actual force in member AE, so the force that's in this member, is 4,041.45 pounds. Now I got a negative answer. So what does that tell me? It tells me that when I assumed tension, that this member was pulling away from this joint, I was wrong, and it was actually in compression. So to draw this correctly, I would have had this arrow pointing in towards the joint. So that tells me, and I'm going to make a note here, that this member is actually in compression. It's not in tension. It's 4,041.45 pounds compression. So I know for a fact that this member is being squeezed together when these external forces are applied to this truss. So we still have one more equation of static equilibrium that we can apply to this joint here, and that is sum of the forces in the x direction. Now that we've solved for one of our member forces, we only have one unknown in the x, and we can actually use the equation. So I'm going to do sum of all forces in the x direction equals 0. And so what are our x forces? We have an AB to the right, so that's force AB pointing to the right, plus AEX, plus the x component of force AE, okay? So AB is just a horizontal force. I can leave that as AB. But AEX, remember how the x component of force AE is actually AE times the cosine of 60 degrees. The y component was AE sine 60. The x component, AEX, is AE times the cosine of 60. And all of that adds up to 0. Well, remember, we already know force AE. We solved for that. That's this number. So I'm going to plug that in. So we have AB, and that's a negative, so it's going to be minus 4,041.45 times the cosine of 60 degrees is equal to 0. And so if I bring all this to the other side of the equation, so if I just add it, I would get my answer. So that means AB is equal to positive this number, okay? So I'll take my calculator and I'll type in 4,041.45 times the cosine of 60 degrees, and I get 2,020.73. 2,020.73 pounds. And this time I got a positive answer. So the force in member AB, which is this member here, is 2,020.73 pounds. And because it's positive, that means I was correct to draw it pointing away from this joint. I was correct to assume that it's in tension, which means I'm going to write a T next to it to tell myself that this member is actually in tension. So now I finished analyzing joint A, and now I know the force in this member AE, and I know the force in this member AB. And so now what I'm going to do is I like to draw what's called a summary truss. And the summary truss is a way to summarize our results as we go. So I just sort of quickly recreate the truss that we started with. And remember, it's something like this. It has 1, 2, 3, 4, 5 joints. And remember, this is A, B, C, D, E. And so far what we know is member AB is 2020.73. And I'm going to write tension, T. So I know this force. And we know member AE is equal to 4,041.45. And for this one, I'm going to write a C because that one's in compression. And because I've identified compression, I can drop that negative sign because the negative just meant that assuming tension was wrong. And so once I correct that and say compression, it's a positive value. So this one's being squeezed together, this one's being pulled apart, and now we're ready to move on to the next joint in our analysis. And I think that joint E is a good candidate because now that we know this member, there's only 2 unknown forces at joint E, and that one is possible to solve. Okay, moving along to joint E. So we're going to analyze this joint that's up on the top left corner of the truss here. And so if you look at joint E, I'm going to try to draw all the forces acting at it. There is a 1,000 pound force downward, which we don't want to forget. That was the external force acting directly at joint E. Remember that there's member DE that's attached to joint E, so we have to draw this member. And we're going to assume that it is also in tension because we always assume tension. And so I'm going to say that's member DE, that's the force in that member. And there's also member BE, so that member is acting, it has a force that's acting at joint E. And we're also going to assume that that one is in tension, so that's member BE. Now, we do have member AE, but remember, we already solved for that one. We said that member AE was 4,041.45 pounds, but that one was already found to be in compression. So here's where it gets tricky. Because we already know that this member AE is in compression, because we know that, we're going to draw it pointing towards the joint rather than assuming it's in tension and drawing it away, because we already found this force, okay? And so I can write that is equal to 4,041.45 pounds. This is now a known value, and we know that it's in compression. Now I'm going to draw a little dashed line here because I know that through geometry that this is a 60-degree angle and that this is also 60 degrees as well. And so we know these angles, and now we have all the information that we actually need to solve for these 2 unknown member forces. So remember, the first thing you want to do is look for any diagonal forces and break them into an X and Y component. So I actually see 2 diagonal forces here, and so I'm going to call this AEX. That's the X component of force AE. And this one will be AEY. That is the Y component of this force AE. And then I can do the same thing to this force BE, right? So BE can be broken into a BEX, BEX, the X piece of this diagonal, and it can be broken into a BEY, the Y component of this diagonal force BE. And so now if you look closely, how many unknowns do we have in the x direction? And so I actually see a lot of unknowns in the x direction. Well, there's two, BEX and DE. These are both unknowns. I do know AEX because I know AE, which means I also know the x component of it. So I have two unknown x forces, which means I cannot start by doing some of the forces in the x direction. But if I look in the y direction, I only have one unknown force because AEY is known since I know this force AE. So BEY is the only unknown y force, or the only unknown vertical force, which means I'm going to want to start by saying sum of all forces in the y direction equals 0. Okay, so what do I have in the y direction? I have a 1,000 pound force going downward. So I'm going to write negative 1,000 pounds. And remember, downward is the negative direction, so that's why I'm calling it negative. I also have AEY, which is pointing upward, so that's a positive, so plus AEY. And I also have negative BEY, so minus BEY. And all of that equals 0. So this is adding all my y forces and setting it equal to 0. So just recopying this line. Remember, we know AE is 4,041.45. So this is plus 4,041.45. And remember, it's the y component, so that's going to be times the sine of this angle. So times the sine of 60 degrees. And then minus BEY. Remember, BEY is also going to be BE times the sine of 60 degrees. Okay, so here's where I'm at. So what I would do is add this to the other side of the equation to get it by itself. So we have BE times the sine of 60 is equal to all of this stuff added together. So I'll take my calculator and do negative 1,000 plus 4,041.45 times the sine of 60 degrees. I get basically pretty much exactly 2,500 pounds on the dot, 2,500. And so to solve for BE, just divide both sides by sine 60. So we get BE equals 2,500 divided by the sine of 60. And so if we do this math, 2,500 divided by sine 60, we get 2,886.75. 2,886.75 pounds. Now I got a positive answer. So that tells me that when I drew BE pointing away from this joint, when I assumed it was in tension, that was correct. So I'm going to write a T next to it to remind myself that yes, member BE is actually in tension. So now we've solved for this member and there's only one unknown member left, and that's member DE. So to solve for the unknown member in DE, we can now use the sum of the forces in the x direction equals 0. So I'll use my other equation. And so what forces do I have in the x direction? I only have these three. So AEX, that's positive because it's pointing towards the right. I have BEX, also positive because it's pointing right. So plus BEX. And I can add DE, also pointing to the right. And the sum of all those forces is equal to 0, okay? So AEX is AE times the cosine of 60 degrees. So that means it's this number, 4,041.45. Times the cosine of 60 degrees. That's my AEX. Well, BEX is BE, which is now solved. So it's 2,886.75. So plus 2,886.75. Again, times the cosine of 60 degrees, because the x component will always be times cosine 60, or times the cosine of the angle, plus member DE, which is unknown. All should add up to 0. And so this is pretty easy because if I subtract both of these to the other side, that will be my answer for DE, and I'll be done. So I'll have DE equals, and it'll just be negative 4,041.45 times cosine of 60 degrees minus 2,886.75, also times the cosine of 60, and that's my answer. So I get negative 3,464.1. Negative 3,464.1. Let me double check. 3464.1. Yep, and that's in pounds. And so I'm going to box this. Now, remember, my answer came out as a negative, which means that drawing it in tension was incorrect. And so this tells me it's actually in compression. 3,464.1 pounds in compression. So now I can go to my summary truss, and I just solve for member BE, which is this member here, and I know that's 2886.75. And that one is in tension, so that's this one here. And I also just solved for member DE, that's the one on the top, 3464.1. And that one's in compression. So I have 2 compression members and 2 tension members, and I only have 3 members left, and then I'm fully finished with this problem. So where do I want to go next? Well, if I go and analyze joint C now, that will knock out 2 more members, and I'll just have 1 left. So I think joint C is a good choice, and that's where I'm going to go next. All right, so moving on to joint C, what's going on at that joint? Here's what we have. There is a 4,500 pound force pointing upward. Remember, that was the reaction force at holding up this joint. And then we have member CD, which is a diagonal force that should be something like this. Again, we're assuming tension because we always do. If we get a negative answer, we know it's actually compression. And then we have this member BC that's hooked up to joint C. So that we're going to call that BC. Also assuming that one's in tension. So we have 2 unknown members here. And again, member CD is a diagonal force, so we are going to break it into an X component, so that's CDX, and a Y component, CDY. And so you could probably tell if you looked at these forces, there's only one unknown in the Y direction, CDY, and there's 2 unknowns in the X direction. You have BC and CDX. And so because there's only one unknown in the Y direction, we're going to start by doing sum of all forces in the Y equals 0. And so what do we have? We have CDY plus 4,500 pounds equals 0. And that's it. So it's a very basic equilibrium equation. Remember, CDY, this is a 60-degree angle, as we saw at the beginning. So CDY is CD times the sine of 60 degrees. So I can change that to CD times sine of 60. And to solve for CD, I'm going to subtract 4,500 to the other side and then divide by sine 60. So CD is equal to negative 4,500 divided by the sine of 60. And so I can type that in the calculator. Negative 4,500 divided by sine 60. Negative 5,196.15. And so that is that's a negative answer. So that tells me that assuming tension for member CD was wrong, this is actually in compression. So I'm going to put a C here for compression. So now that I've solved for one of the members, I can now move on to the other member and try to solve for the force in member BC. So I'm going to use my other equation. Sum of the forces in the X direction equals 0. And both of my X forces are pointing to the left, so they're negatives. So I have negative BC minus CDX equals 0. That's all the forces I have in the X direction. So it's negative BC, and remember I just solved for CD, that's negative 5196.15, but I have a negative. I'm subtracting a negative, so 2 negatives makes a positive. So this is plus 5196.15. And so remember, CDX is times the cosine of 60 degrees. So times cosine of 60 equals 0. And so to solve for this, I can just move this BC to the other side. It will become positive. So I have BC is equal to this times this. So we have 5196.15 times cosine of 60. And so member BC is 2,598.08. 2,598.08 pounds. And just to double check, 2598.08. Okay, so that is in tension because it came out as a positive answer, which means that when I drew BC in tension, that was a correct assumption. So I'm going to put a T here to show this member is in tension. Now that I solved for both of these, I'm going to go back to my summary truss and let's add these new values. So CD 5196.15. And that is in compression. And then we have BC, which is 2598.08. And that one is in tension. So now we have almost every force finished. There's only one more left. So I really have two options here. I can go and analyze joint B to find this unknown, but B is still looking very crowded. There's a lot going on there. So I think I'm going to just move to joint D, figure out this unknown force, and then I'll be done, and I'll have no reason to ever have to finish at joint B. All right, so now we're at our very last joint. We're going to analyze joint D, and then we will be finished. So joint D has, if I were to draw it, here's the joint. Let's label this D. It does have a force, this diagonal force, which is member CD. And actually, we solved for CD and said it was in compression already. So I'm going to redraw this because I know that CD is in compression, so I'm going to draw it towards the joint. I don't need to assume tension anymore because I already know that number. In fact, I know that CD is 5,196.15 pounds, okay? And then what else do I have? I have a 3,000 pound external force at this joint. That's this force here. I also have member DE. And so DE was also found to be in compression, which means I'm also going to draw this one pointing towards the joint because I already know it's compression. I don't need to assume tension and draw it away. And that one has been solved for. It's 3464.1 pounds. And finally, I have member BD, and this is actually the last unknown in this problem. So member BD, because it is unknown, I'm going to draw that in tension. I'm going to draw that pointing away from the joint, okay? And I'm going to add this dashed line in because I do know this is a 60-degree angle, and I know this is a 60-degree angle, okay? And that is actually all the information I need now to solve for this joint, okay? So let's start with sum of all forces in the, should I do X or Y? Well, let's break these forces into their components first. So CD has a CDY part, and it also has a CDX. This is CDX, the horizontal component of force CD, and CDY is its vertical component, right? And then if you look at force BD, it also has a BDY, the vertical component of this diagonal force, and it has a BDX, which is the horizontal component of this force BD. So now I have every force that I need, and these are known because I know force CD, and these are not known because I don't know force BD. So that means, if I think about it, the best place to start here is probably, it actually doesn't matter. I have one unknown in the X direction and one unknown in the Y. So either way is a valid place to go. I'm just going to do sum of the forces in the Y direction equals 0 because that's what I'm used to. Okay, so we have a 3,000 downward, so that's negative 3,000 minus BDY minus, not minus, plus CDY because that one's pointing upward. And I believe that is all the vertical forces I see here. So all of that has to equal 0. So we have negative 3,000 minus BDY. And remember, that's the same thing as BD sine of 60. And then plus CDY, which means CD sine 60. But remember, we know CD is 5196.15. So plus 5196.15 times the sine of 60 degrees, and all of that has to add up to 0, okay? So what we have is if I were to bring this BD sine 60 to the other side of the equation, I would have positive BD sine 60. Let me just cut this off. Okay, equals what's all on the left side of this stuff. So basically negative 3,000 plus this number. So we have negative 3,000 plus 5196.15 times the sine of 60. And all of that comes out to be 1,500 on the dot. And actually, I'm going to need more space here. So now I can divide both sides by sine of 60, right? And that's going to give me my answer. So BD is equal to this over this. So 1,500 divided by sine of 60, I get 1,732.05. Now I did get a positive answer here, so that tells me that when I assumed tension for BD, that was correct. So it is in tension. And since I did just solve for my last unknown, there is actually no reason for me to do the sum of the forces in the x direction because I'm done. So I can go to my summary truss and I can add my final force, 1732.05, and that's this one here, 1732.05 pounds, and that one is in tension. So now I've successfully solved for every single internal force in this truss. I know that this one, and this one are in compression, and I know that this, and this are all in tension. So some are being squeezed together, some are being pulled apart, and they're all experiencing different forces because the external loadings at the start were uneven. They were asymmetrical, okay? So it's a very complicated, very involved process to solve for this truss. It does take a lot of work, but it's very satisfying when you get to the answer. And remember, we made a lot of assumptions to simplify this problem. Without those assumptions, this would be exponentially harder. Thank you for watching Phantastic Physics. Please like this video and subscribe to our channel if you want to see more interesting physics content. Goodbye for now, and remember, it's a fantastic universe out there, so stay curious.